Good. Okay. So we've got a point 8 units from the origin here. And another point that's 9 units from the origin. And there's a tenth of a radian between the angle from the line from the origin to this point and the radial line to this point. Okay, a line from the origin is a radial line. Okay. So how far do you think you got to move here? I think if you move 1 unit here, you'll be pretty close to straight across to this point. I say, let's do an estimate. Not be too technical. And let's not get into a lot of calculations. Let's just do an estimate. So what we're going to consider is what happens if this angle becomes very small. And the smaller this angle is, the closer we are to being, the closer this angle would be to being a right angle. A tenth of a radian is somewhat less than what we got right there, actually. Okay. So we're pretty close to having a right angle. Then the question is, how do we get from here to here? All right. I did see one picture that's relevant to this. So I'm going to say we move 1 unit. That vector is going to have length 1. Then I'm going to draw a circle. A tenth of a radian angle. What should the radius of this circle be? Can you show me with your fingers? I'm going to use this circle to estimate the length of that vector. So what should the radius of the circle be? Radius circle would be 1, that'd be down here. That wouldn't correspond to well with that. I want the arc to correspond pretty well to this distance. My radius would be. Where should this circle be in this picture? Yeah, the circle should go through this point or this point. Either way, it's going to have a radius of 9. Does that make sense? We want to have that picture. Picture central to something that's kind of hard to understand in little quarters. Okay. Okay. And it comes up several times. All right. So we want this circle to have radius 9. Okay, so what's this distance here? Right here is my new distance. How far is this approximately? We'll talk about it. Okay. This is a formal definition. I'm just giving you the idea. Right there's the radius. Okay. And we'll use blue again. The yellow. There's the radius, R. You have to walk further. If you wanted to walk from here to here, you wanted to walk around the circle, along the circle from here to here, which distance is greater? Radius or the length of that arc? How many think the radius? How many think the length of the arc? I disagree with you. I don't believe this thing.
I mean, if it wasn't the scale.
Huh?
The scale of it. Like if it was.
Yeah. this is this long, right? Now, without changing my fingers, I'm thinking that that length is about here. So I think this is further than this. Okay? So I have to tell you, I don't want to be out in the back country estimating distances with you people. Okay. Let's walk that mountain over there. It doesn't look that far away. You might get away with that in the east if you're out in the west. And I've never been out in the wilderness in the west, so good thing I couldn't be here today. Oh, but, okay, you get the idea. I think it's pretty obvious that this length is bigger than this length. So I want you to draw me a picture where the radius is equal to the arc length. Yep. Well, don't use anything you think you know. Just draw me an intuitive picture where the radius is greater than the arc length, where the radius is equal to the arc length. Now, you know what I wrote on the board. You don't have to write that down yet, but I did write that the radius here is greater than the arc length, right? And watch, I can prove, right there. It's one end of the arc to the other, right? Now the arc is curved, so it's a little further from the length of that chalk, but not much. If you walk directly from here to here, and I walk directly from here to here, you might be a step ahead of me by the time we get done, but not far. And right there is the radius. Knock that finger out of the way, okay? And the radius is considerably longer than this red piece of chalk. So, to my eye, it was clear, but I'm more used to looking at these things than you are. Okay, so let's see if you got a radius equal to the arc length. You know how many times you got to hit the record button before the record. Press it. Okay, so here. Here's the surface. You first draw a half decent circle. I'm not looking for perfection here. I'm demonstrating perfection, but I'm not. And then the center, wherever the heck the center is, maybe it's about there, okay? So, if you're going to draw a circle and draw the bullseye in the middle, okay? And then draw a radius in any direction you prefer. It goes from the center to the edge of the circle, right? Now that radius is somewhat longer than this piece of chalk. So I'm going to try to draw an arc that has the same length as the radius. I'll draw it in the color of the contrast a little more. Okay, so let's say I draw an arc this long. The distance along the arc is a little greater than this point-to-point distance here. Anyhow, that's about the length of the piece of chalk, right? Can you see that? The radius is quite a bit bigger. It's pretty much about like what I drew here. So I probably want to go out to a point that's almost as far from this point as the length of the vector. I'm going to say, I'm going to try this. Okay, maybe just a little bit longer. And now it's a little longer than the piece of chalk. That's still quite a bit longer. And straight line distance is still pretty close to the arc distance, right? But of course, the bigger the arc is, less as so maybe here. Okay, so there we have it. Here we have, I might have gone a little too far, but that's in the right ballpark. Okay. Now, if I've got the radius it's not a totally well-defined statement, but the arc length is equal to the radius, okay? I won't get it all over the place. That would be a 1 radian angle. Okay. So what's the total arc distance around the circle? It's 2 pi r. Because I don't know how to operate chalk. Okay, radius 2, or the arc of a circle is 2 pi r. So a circle corresponds to 2 pi radians. I don't even bother to write 2 pi radians because radians is automatically the unit of an angle. If you want an angle in degrees, you write degrees. Want an angle in grads, you write grads. It's like 100. I think. If you got the angle in some other unit of measure, you measure angles in any unit you choose. Okay, you got to put that unit in. If it's in radians, you don't have to put a unit down, but you can. So I could say 2 pi radians, but I'm just saying 2 pi. See an angle without degree or radian on it, even if you're an engineer, you lie. Because you do degrees and you don't write the degrees. Engineers do that all the time. So they get confused between degrees and radians. Sometimes engineers don't need radians, often they do. So just be aware of it. You can follow the bad habits of engineers worldwide. You know a lot of things that I don't. But one thing they don't know as well as I do is you really got to be conscious of your units. Otherwise, you crash your spacecraft into Mars, which somebody did for several $billion because they didn't get the units right. Okay. Okay. It's right. That was before most of y'all were born. Thankfully, any of y'all were born. Nobody looks at it. Okay. Now, doesn't seem long ago to me. Neither is the last ice age. Okay, so it's way too much time we just spent talking about what a radian is. You've gotten this far without learning what a radian is. No offense, you haven't been paying attention. I got almost as far before I finally figured out what a radian was. It's very simple. It was never taught about. That's why nobody knows how to do it. And I'm also teaching it poorly, so you still learn. There it is. Now, my point is, this is the 10th of a radian. What's the radius of the circle? What's the radius of the circle? It's 9. Why is it 9? Because it's going through this point. Something wrong through this point, I guess. Not exactly. Okay. So, how far is that? You got a 1/10 of a radian angle on a circle of radius 9. What's the arc length? breaking this down. If a 1 radian angle gives you an arc equal to the radius, what does a 1/10 of a radian angle give you? Gives you an arc equal to 1/10 of the radius. Okay? Now there are formulas, and the problem, the reason people never understand radians is they're taught to memorize these formulas that are so confusing, nobody can keep them straight until they understand what a radian is. And then the formulas are so obvious, you don't need them. Okay? So I don't even talk about these formulas. I think they cause more harm than good. So we reason that if on a circle of radius 9, you had an arc of 1 radian, if this is a circle of radius 9, that would be 9 units. If it's 1/10 of a radian, well, it'd be 1/10 of that arc, which would be 0.9 units. Now there's a formula. Okay. Delta S equals R delta theta. Then they have you memorize the formula delta theta equals delta S over R. And immediately you're confused as heck. You got 2 equivalent formulas that come about from a trivial algebraic step. Screw that. Okay. 1 formula, but you don't need the formula if you understand what a radian is. If you understand what a radian is, you can always write the formula. So why even memorize the stupid formula? Learn what a radian is and think in terms of what a radian is. Okay? That's central to what we want to cover today, and we've spent way too long. But you need to know that, to understand what's coming. Okay? And coming here in the next hour. Okay? It's 44 minutes. Okay. So what I'm saying then, that this distance is approximately 0.9. This distance would be approximately 1. Now, really, you'd have to follow an arc of length 0.9, which is going to be a tiny bit longer than that arrow of length 0.9, right? And we're thinking we want to find the arrow. Or we want to approximate the arrow, but if the angle's small, the arc and the straight line distance, as I established when I was talking about this, are practically identical. Okay, so now I'm going to say something like this. Okay, here is our theta. We'll make it a vector because I used this kind of language with the problems I gave you a week and a half ago. Okay. We've got R theta plus delta theta. And we want to look at what's happening here. Well, our angle is what? What's the angle between these two? It's delta theta. If you go from theta to theta plus delta theta, your angle between the two is delta theta. Then, from the tip of this vector, the tip of this vector, I say that you have to move a distance equal to, very close to delta R, which is R of theta plus delta theta minus R of theta, right? R almost looks like a V in context. So we're going to let it start. Okay. And then this distance is, well, in terms of theta, delta theta, and r of theta, what's this distance? Okay, a lot of people kind of stare at the picture, trying to get an idea. I didn't give you much time, and that's naturally the way it starts. Okay, usually by this time I'd be drooling. Okay, now, if I was in class, but, by now, do what we did here, what are we gonna do here? So we're gonna draw a circle, right? What should the radius of the circle be? It doesn't matter much if delta theta is small, because there's not gonna be much difference between r theta and r theta plus delta theta. So I don't care what radius you use. You could use a radius of any angle between here and here. I mean, you could use r of any angle between theta and theta plus delta theta. Now, r of theta, this means this is a function of theta, this is a function of theta. Okay. Maybe r is equal to, maybe r is, okay. What I'm saying then is that this distance here should be equal to approximately r delta theta, shouldn't it? They don't even call this an r asterisk. Take any r between this r and this r. If theta is small, there isn't much difference, right? Draw your circle. Then you have angle delta theta on a circle of radius r star. If you have a delta theta on a circle of radius r star, just the same as if you have a circle of radius 9 with an arc of 1/10 of a radian, you multiply the radius by the angle. The radius is r star, the angle is delta theta. So you could draw this picture of this situation. And I recommend that you go home and do that. Okay? Make yourself a note, whatever. All right. Well, that's a big deal. If you understand that, you understand something that people in multivariable calculus classes often don't, even at the end of the course. So it's a big deal. I don't know if it's worth 45 minutes, but yeah, 44 minutes, not that much. Actually, we started a little late, about 41 minutes. Okay. Well, again, that's kind of central to the main result of the last three sections of chapter 1. Now, the first section of chapter 1 is on polar coordinates. Have you had polar coordinates in your classes? Have you drawn polar graphs? You know how many polar graphs I drew before I was 15 years old? In standard curriculum, I wasn't accelerated or anything. There was a graduating class of 250, and in a class of 50 out of the 250, everybody did this. This is during the early days of space. Now we've got an AI race. Okay, I don't know where that's going, probably into space. Okay, all I'm saying is it's hard to teach multivariable calculus when you don't have the background. If you don't know about polar coordinates, there's a significant deficiency in your background. Fortunately, what I'm going to ask you to do with polar coordinates is not that tough. I'm just going to give you one example. Okay? And you can work out the rest because they're in the homework. And I'm not going to ask you to do the symmetry tests at this point. It can get a little confusing. The rest of it isn't too bad. Okay? It's really not difficult. Okay. So, in polar coordinates, you're given R as a function of theta. You can think of a vector R because it just directly translates into some of the stuff you've done with vectors and what you've just done with vectors. Okay. Let's just say you've got an equation like this. R of theta equals 2 cosine theta. Okay. I'm going to draw. Oh man, that's a bad idea. Never draw your axes before you draw your circles. You think I'd know that after teaching for 100 years? Okay. These are getting pretty distorted and everything. You know. Okay, this circle here is where R equals 6. Obviously, R equals 0 here. R equals 1, 2, 3, 4, 5, 6. Oh, sorry, it's R equals 7. Can't count. I thought these two were the same one. Okay. Now it's not a very good picture. You have good pictures in your book. You need to get polar graph paper. You know, you can get some, get hundreds of websites and let you print out polar graph paper. Okay. And it pretty much looks like this, but the circles are much better. Okay. So if R equals 2 cosine theta, let's just make a table. And I don't really got room to go from 0 to pi, but usually we'll go from 0 around to 2 pi, right? Okay, so here are the angles we want, right? Pretty much got them. Here's pi over 4, 2 pi, 3 pi over 4, pi, right? Now, what's the cosine of 0? Know the trigonometric functions as a function of the circular angle. Don't draw that because it's something you don't always think about. Remember that the cosine of theta is the x coordinate of the area on the circle, where this is a unit circle. So this is a unit circle. There's 1, there's 0. That looks like about 0.6, and that looks like about pi over 4, right? But of course, you know that the angle pi over 4 gives you sine and cosine both equal to the square root of 2 over 2, which is about 0.7 over 7. So picture's not totally accurate. But if I tell you that the cosine of pi over 4 is about 0.7, and let's just say 0.7, which be a little more accurate, then it's reasonable in terms of this picture, considering this picture is hand drawn, right? Line might be a little too big. My circle might be a little lopsided, although they both look perfect to me. Okay. Now, just by visualizing the circle at angle 0, you're here, and your distance, you're on the x-axis, and the x-coordinate is 1. At pi over 2, you're here, and the x-coordinate is 0. At 3 pi over 4, you're over here, and the x-coordinate is negative 7, 1. And incidentally, x squared 2 over 2, you should know how to do all that. And now you're at negative 1, right? Okay, so this tells me that the polar graph of this thing, when theta is 0, r theta is 1. Well, where's theta equals 0? That's here, right? And r is equal to 1. Okay. Now, I'm going to change my function. 7 cosine theta And I'll multiply each of these by 7. Some of them I just indicate the multiplication. You know, that's pretty close to 5, right? 7 times 0.71. Okay. So now if theta is 0, if this is a function, you've got r equals 7. That means you're here. Okay. On pi over 4. It's about 5. So we got out 1, 2, 3, 4, 5. And there's a point. When we get out to theta equals pi over 2, r is 0, which puts us right here at the origin. Because that's where r equals 0, right? Then if we go to 3 pi over 4, that's here. R is -5. First 3 pi over 4, 3 pi over 4 is here. What's -5 there? Well, we got to go back this way. So 3 pi over 4. R is -5. Any of that make sense? Those are the points. If you do all these points, and find out graph is a short. Okay, get the idea? Very simple to plot points and graph these things. Now, if you got cosine of 2 theta, the whole thing ends up looking something like this. And if you keep going, it kind of does this. Because 2 theta is going to go from 0 to pi between here and there, right? Which means r is going to go from 1 to 0 as we go from this angle to this angle. To get from 1 to 0, it does something like this circle, but it goes through the values a lot faster, and it does this sort of thing. Then when it comes back around, it does this. Okay? And maybe it looks like that, maybe not. Look at the examples in the book. That's a review of what you should have learned by the time you were junior in high school. Okay? By the time you took a pre-calculus. It should have been part of your pre-calculus course. It is in the curriculum as part of pre-calculus. It's in the second semester. How many of you took it as a dual enrollment course? Well, you didn't get to. You didn't do it. Okay? Now, if you took it somewhere else, I don't know. It gets left off. It's essential. You can't start multivariable calculus unless you know it. Fortunately, it's pretty easy to learn what you need. There's symmetry tests. They're important. We'll talk about them later. Once you get familiar with polar coordinates, it gets pretty easy to do symmetry tests. Now, you can take an equation in polar coordinates and change it to rectangular coordinates. Okay? Polar coordinates. You can do the opposite too. So if this isn't totally obvious to you, then do more work with the unit circle. Go back to that pre-calculus text, chapter 5, I believe, which introduces the trigonometric functions in terms of the unit circle. just read it, you'll probably understand it without having to do all the problems. But you gotta do problems, find time, budget it at least over the next few weeks to get the stuff up to speed, because I need every bit of it. Okay? So we could say that these equations convert polar coordinates to rectangular. So if we have r equals 7 cosine theta, how do we convert this to rectangular? Well, you'd have to know theta in terms of r, right? We'll do that in a minute. And you just solve this for theta. You get the inverse cosine of x over r, the inverse sine of y over r. Okay? Let's say you have the equation x squared plus y squared equals 8. To convert this to polar coordinates, you're going to write or cosine theta for x, or sine theta for y equals 8, right? Take a couple steps, and you get r equals 8. Sorry, you get r squared equals 8. I'm not going to comment further. That's trivial. If you have a polar equation, you can substitute. If you have a rectangular equation, you substitute these things. Now, the algebra can get much trickier. If it was 2x squared plus y squared equals 8, then you'd have a more complicated polar equation. You'd have an ellipse, major axis of 2, minor axis of 1. Okay. Now, if you want to convert this equation, first of all, you say, well, then you know, I'm actually not like to read that because it's a little more complex. One thing you can say is that x squared plus y squared is r squared, but there's a lot more things you can do, like I don't want to get into the detail. Simple substitution, you can look at examples. Okay? Because we've got to talk about the real stuff. This is review of high school. So you got to get that up to speed to an extent. You shouldn't have too much trouble. Okay, in polar coordinates, I want the arc length. Back to this. Delta R is this, right? And the magnitude of delta R is then this distance plus this distance, right? L is then okay. First of all, I've got delta R here. And I've got R delta theta here. Now delta R this big word here, differential. The idea of a differential, the official differential looks a little different. But delta R equals I'll just say delta R. It'll be the magnitude of delta R. Now I'm going to write. I don't want to explain everything I'm doing. Take too much time. I'm going to write delta R without the vector, and it equals R prime delta theta, where R prime is dr d theta. Okay. That should be familiar from calculus. Go back to the section on differentials. So the magnitude of this delta R thing is your delta R without the vector, and it's approximately equal R prime delta theta, or dr d theta delta theta. Now, if you accept this, then you understand that since this is almost a right angle, why is it almost a right angle? It's because the arc of the circle is perpendicular to the radial line. Okay. So this vector here is almost perpendicular to any vector between here and here. Okay. Perpendicular to some vector between here and here, but it's very close to being perpendicular to all these vectors. So this vector can be assumed to be at an approximate right angle. This angle is near 90 degrees. And this distance here is the distance along the arc that goes from here to here. Okay. I didn't draw that in there. I'm throwing it at you here. Okay, so you've got some kind of polar curve. Okay, you might be doing all kinds of things, but it goes through these points. Because it is an R of theta, and this is an R of theta plus delta theta. Okay, so these two points here, the polar coordinates would be theta, R of theta. Where is it? That point would be theta, R of theta. This point would be theta plus delta theta, R plus delta theta. It gets a little heavy in notation, but if you keep coming back to the geometry and the idea of what's going on here, and just come back to this picture and relate everything. It's as simple as delta S equals R delta theta, but the notation looks heavy. Okay. That's all it is. That's what we're saying. We've established delta R by the differential has got to equal this times delta theta. That number. Okay. R prime delta theta When you see prime, you often think derivative with respect to x or t, but I've defined it down here, r prime is dr d theta because theta is the only independent variable we've got. Okay. So we got this. We got this. Shouldn't have a vector over this. It should be just r delta theta. So what is LS? Pythagorean theorem, which I've seen in some of your work already, is this. Okay. And if we factor out a delta theta from the square, I mean, you've got delta theta squares in here, they factor out, and then you take the square roots, you end up with the delta theta outside the square root. You have this. Um, that's your picture. I'll let you read the rest of it. But that's where it comes from. You can see a derivation fairly similar to this. Okay. That's your R place. That's the increment of R place. You let delta theta go to 0 and do an integral. Okay. Now, if you want the area, what's the area of this sector here? Well, that sector is a triangle. Okay, now like from here to here to here to here, right? From the origin to this point, back to the origin. That's the area between the origin and the proof. Okay. That area is there a picture that's on. Okay, here's R theta. Here's a small delta theta. Triangle. Nearly isosceles if delta theta is small, because if delta theta is small, R hasn't had enough delta theta to change by much, right? So for small delta theta, this R is going to be pretty close to this R. And you could use any R between here and here. If it's nearly isosceles, then it's nearly a right triangle because the angle for small, if you got a small angle here and your angles add up to 180, these angles got to be pretty close to 90. Okay. So the area has to be approximately that of the right triangle And the legs approximately r theta and r theta delta theta. And remember, this distance here, perpendicular to this line over to this line, is about r delta theta, where r is some r between this r and this end. Okay. Its area is right theta inconsistent there. It's right like the assumption. Its area is approximately 1/2 r theta delta theta times r theta. Okay. Which is 1/2 r squared of theta delta theta. And the integral is r squared d theta. So for example, we'll do this just make sure I'm not screwing something up. What's the area of this circle? If this is a circle, which I claim it is, its radius is 3.5. Square 3.5, you get 12.25. Okay. And multiply that by pi, you get about 40. So the area of this circle ought to be about 40. So let's apply this to r theta equals 7 cosine theta. What's this mean? This means the integral from 0 to pi, because remember theta went from 0 to pi, and we traced the circle out. Okay. So 1/2 of 7 cosine theta squared is theta. That is going to give me what I think it ought to give. And you got to integrate cosine squared theta, which is you're going to use the double angle form or the cosine squared theta is closely related to cosine of theta. Okay, take that relation, solve it for cosine of theta, and you can integrate the cosine squared. Turns out the integral cosine squared from 0 to pi. Oh yeah, you got a pi on that. That's what pi comes from. Turns out it's 1/2 pi. Okay. So 1/2 pi times 1/2 is 1/4 pi times 7 is 7/4 pi. It's times 49. 49 pi, 12 pi, which is about 40. Now, you can take my words and follow them, or you can do that anyway. I'm using the fact that I know that the integral of a sine squared or a cosine squared over a complete cycle, a complete arc, is half the average value of the cosine over any arc is 1/2. Over a full arc from 0 up to 0. Okay, that's something you work out in calculus. It's worth working out because it comes up a lot. Otherwise, I won't remember. Okay. So it's come up a lot. I mean, I might remember because looking through things, but that's just something, it's easy. It's an easy, it's worth doing. Probably don't have time to do it. Okay. So I estimated that this ought to be about 40. I estimate that interval is about 40. You can verify it. You see where this comes from? We're just adding up all the 1/2 r squared d thetas, which correspond to the areas of all the little approximate triangles you get when you divide up this region. Divide up in a bunch of triangles. Every one of these little triangles. Okay. In other words, partition your thetas. Like I said, partition your thetas, then you get something very close to the isosceles triangle. You add them up and you get the area, and that's all an integral does. Now you have the steps in the integration. We'll talk more about steps of integration, partitioning, and stuff like that. But for right now, you have a serviceable formula. The area of a polar curve. R stands for R of theta. That's how we used it here. R was replaced by the formula for R of theta. So you have a formula that gives you an arc length, a formula that gives you the area. We're just about out of time, so I don't have time to write the formula, the integral for the arc length. But now there's a lot of stuff going on here, a lot of stuff you need to hone up on, a lot of stuff to do, and I understand that. Do your best, try to make at least a shot on each part of it.